So, my name is Madona, and this year I worked on decorating the surface of red blood cells in order to mask them and test the effect of pegylation on red blood cells. So for the past 2 years, I've been working with manipulating the antigens on red blood cells, human red blood cells, in order to attempt to mask them or manipulate them somehow in order to generate universal cells for transfusion purposes. Now, transfusions are a critical therapy in medicine, with approximately 5 million Americans requiring blood transfusions each year. Now, this is due to chronic illness, blood loss due to trauma or surgery, and also sickle cell anemia and thalassemia patients use it to alleviate their symptoms in order to replace some of their abnormal cells with normal cells, or to increase the oxygen carrying capacity of their blood. So in order to perform a blood transfusion, the blood of the patient has to be matched with the blood of the donor, and this is done through a blood typing process. The main antigens that are blood typed are the A, the B, and the D antigens. And this here shows the ABO group. The blood type is determined by the antigens present on the surface of the cell. So this person would be positive for the B antigen because they're positive for the B antigen, they have B-type blood, but they also have A antibodies. If the incompatible blood is introduced into the body, they clump based on shape, and the antibody detects the antigen, the foreign antigen, causing a severe reaction. And this is actually what it looks like. The blood agglutinates, and it can lead to kidney failure or even death. So it's very important that the blood is properly typed. For patients, like I said before, that receive frequent blood transfusions for sickle cell anemia or thalassemia, they tend to develop a disorder and develop alloimmunization. Now, what happens is, with repeated exposure to the foreign blood, they become sensitized to non-ABO antigens, such as the C and the E antigens, that are not as commonly tested for. So this makes it harder for them to find proper blood donors because of the distribution in Rh factors that's not present in all different ethnicities of the donors. So in order to overcome these difficulties, researchers have been attempting to come up with universal cells, or actually ways of manipulating these antigens in order to remove them or prevent the alloimmunization reaction when administering a blood transfusion. So previous methods have included enzymatic digestion, in which enzymes would be added in order to try to actually remove the antigen itself from the cell. However, although it's been successful in removing the A and the B antigens, it hasn't been able to access the Rh antigens, such as the C and the E antigens. Now, this is because of the structure of these antigens. The A and the B antigens are single pass. They pass once and they extend out of the membrane, so they're more easily accessible by whatever antigen whatever enzyme is added to remove the antigen. However, the Rh antigens are multi-pass, so they pass multiple times through the membrane, so therefore they're harder to access and therefore harder to remove. So this project tests a novel approach in order to mask or create a barrier over these antigens, so that when the antibodies are added, they're not able to detect the antigens, therefore making them appear as if they are CE negative instead of CE positive. So in order to test this, I used the pegylation method. And pegylation, as shown here, is the modification of a protein by the conjugation of one or more polyethylene glycol chains, or PEG chains. And you can see the chains being attached here. Now, this polymer is FDA approved, and it's non-toxic, so it's safe within use inside the body. And it also has several advantages, such as prolonged residence inside the body. So the pegylated cells.
Noel White, if you're in the building, please come to the main office.
Noel White.
Noel White, if you're in the building, please come to the main office.
So pegylated cells are able to stay in circulation longer, which is a positive thing for transfusion patients, since they don't need to get transfusions as frequently, since they're able to stay in circulation longer. So I tested two pegylation chemistries. The first is dilation-mediated maleimide chemistry, using polyethylene glycol, PEG 5000 for short, or immunothioline, another reagent used in this chemistry. So the way this works is that the immunogroups on the surface of the protein are modified with the addition of immunothioline to become maleimide reactive thiols, which creates an extension arm that's attached to the protein, and therefore when the PEG is added, it adds as an aid. The extension arm aids the PEG in accessing the protein, and therefore is able to mask the antigens more efficiently. The second chemistry I used was acylation chemistry, using a reagent called HS reagent. Now, this is direct pegylation. It's not pegylation using an extension arm. where I just add the HS reagent directly to the protein to see if it would be able to mask the antigens. So I'm really seeing whether or not the extension arm would help in the masking of the antigens. So last year I worked with masking the A and the D antigens. I did find that these two chemistries were able to mask the D antigens, and since the C and the E are structurally similar to the D, I predicted that maybe these two chemistries could also mask these more rare antigens, the C and the E. So in order to test this hypothesis, I obtained whole blood positive for the C and the E antigens. I isolated the blood components and the plasma from the red blood cells by centrifugation, and once the red blood cells were isolated, I added storage solution until I was ready to use the blood cells. The treatments were added in two different groups that tested two different chemistries. The charts are actually on the second page of third page. So the first group received the PEG 5000 and immunothioline testing the methylation chemistry. I tested 4 samples in total, 3 different concentrations and the control. The second group tested the direct pegylation or the acylation chemistry using the HS reagents in the same concentration levels. So once I added these reagents, I rotated the samples for 2 hours in a sample revolving rotator mixer in order to properly coat the cells with these reagents. And after that, after 2-hour incubation, I washed the cells and I diluted them in order to prepare them for the agglutination assay. And the agglutination assay was able to tell me whether or not the masking was successful. And I graded it based on this system right here. If the antibody is able to reach the antigen, there will be clumping or agglutinations present, like as shown here. But if the antibody wasn't able to detect the antigen, indicating successful masking, then it would mean that the masking was successful and the pegylation procedure was successful. So I rated them on a grading scale of 0 to 4. 0 would indicate successful pegylation, and a 4 would indicate unsuccessful pegylation, since the antibody was able to detect the antigen. And these were the results that I got. These are for the HS reagents testing these chemistries. So the control sample received a rating of 4 as expected, since no treatment was added. However, as the concentration increased from 2 to 10 millimolar HS reagent, the rating steadily decreased, eventually reaching a level of 0, showing individual blood cells. And this is shown here. The control has agglutinations present. However, as the concentration increased, you can see individualized red blood cells, meaning that the antibody wasn't able to detect the antigen at all. Same thing for the other samples. As the concentration increased, it wasn't the antigen, the antibody wasn't able to detect the C or the E antigens. For the samples treated with the polyethylene glycol and immunothioline, similar results were shown, where as the concentration increased, the rating significantly decreased, and there were similar results shown here for both the C and the E antigens. So it was concluded that both chemistries are successful in masking the C and the E antigens completely. So not only would I have to, in order to maybe look for something that would probably help for transfusion purposes, not only would I have to see if these chemistries are able to mask these antigens, but also how do these chemistries and how does this pegylation method affect the cell's structure and function. So for this, I ran 2 additional assays called the oxygen affinity and zeta potential assays. Now, zeta potentials measures how readily...
Malika Foster, if you're in the building, please come to the main office. Malika Foster, if you're in the building, please come to the main office. Malika Foster, to the main office.
Okay, so oxygen affinity measures how readily the hemoglobin in these cells is able to acquire and release the oxygen. So in order to test oxygen affinity, I added the samples to a hemox analyzer at 37 degrees to simulate physiological conditions. I flushed the samples with 25% oxygen first, and then flushed them with nitrogen in order to dissociate the oxygen from the cells. And from there, I obtained the oxygen dissociation curves. I was looking for 2 main values, the P50 value and the PO2 value. The P50 measures the partial pressure of oxygen when the sample is 25% saturated with oxygen. And the higher the P50 value, the lower the oxygen affinity. So I was looking to see, compared to the control, if there were any changes in oxygen affinity for the cells that were pegulated. In order to interpret these graphs, I looked for characteristic shifts. A left shift would show an increase in oxygen affinity, but a right shift would indicate a decrease in oxygen affinity. As you can see, for the group testing HS reagent, there was no shift even at the highest concentration. So that means that the oxygen affinity wasn't significantly altered. And this is also shown by the P50 values. Compared to the control, the HS reagent, even at the highest concentration, did not significantly alter the P50 value of the sample, meaning that the oxygen affinity wasn't altered. However, for the PEG and the immunothioline samples, compared to the control, the P50 value decreased from a rating of 17 to about 8 or 9, which shows a dramatic drop in the P50 value and a dramatic increase in the oxygen affinity of the cells. Now, it was not very clear why this happened. It's not known whether or not immunothioline is membrane permeable. However, we do know that the PEG and the HS cannot penetrate the membrane, but the immunothioline was probably able to enter the membrane and alter its characteristics, and that might explain why the oxygen affinity was significantly increased because of this reagent. Another thing I tested with oxygen affinity is the Hill coefficient, which measures cooperative binding inside the cells. As one monomer of the hemoglobin absorbs the oxygen, it makes the subsequent monomers absorb oxygen at a faster rate. So a rating that's greater than 1 shows positive cooperativity. And there was, the samples showed a level that's greater than 1 for the HS treated samples, and they were in a similar range to the control. For the samples treated with the PEG and immunothioline, the numbers decreased also significantly, and that might be explained by the increased oxygen affinity. Since these treated cells were able to absorb oxygen more readily, there was no need for the cooperative binding, so that's probably why the numbers are significantly lower. So another assay that I ran was the zeta potential assay. Okay. So another assay that I ran was the zeta potential assay, which measures the overall charge or stability of the cell. It's very important that the zeta potential is maintained because if it's significantly altered, it could cause changes in the charges of the cell. So the higher the zeta potential, the more the cells are able to repel each other. Since human red blood cells have a naturally negative charge, they're able to significantly repel each other, and it makes them stay in dispersion and also resist aggregation or agglutination. And the lower the oxygen affinity, the more the cells are not repelling each other, so they're able to aggregate more, which is negative because if these cells were to be transfused, it's important that they stay in dispersion and maintain their negative charge so that they don't interact with the negative cells. So I tested this using a zeta potential analyzer, as shown here, and I ran each sample for 10 cycles and took the average. And the results were shown here. As you can see, all the samples treated with even the highest concentrations maintained the negative charge of the cell, which is very important because it shows me that the zeta potential wasn't significantly altered by the pegylation procedure. So since the negative charge was maintained, it shows that the cells were still able to remain dispersion, repel each other, and resist aggregation, which, like I said, is very important for transfusion.
The order from the restaurant is here. Whoever ordered the food is here.
Sorry, let me just go back. Okay. So my results show that both the alkylation chemistry and the methylation-mediated maleimide chemistry were able to mask the antigens on the cell successfully and create CE-negative cells from CE-positive cells, which is something that's very positive because the antibodies weren't able to detect the antigens, and therefore they were able to mask the antigens. Also, the oxygen affinity and the zeta potential were not significantly altered, which are positive results because if cells were to be transfused, it's very important that these characteristics aren't altered in order that would interfere with the oxygen affinity or the charge or stability of the cells. So hopefully this could contribute to a larger body of work that can hopefully result in one day patients receiving these modified red blood cells in order to prevent the allomerization reaction and increase the supply of universal blood.
I'm just gonna start.
Oh my god.
Okay,
Stop the
so
video.
you are